In this question, we are given part of our steam turbines, that is a Prium 2026 exam. So we are given on question number 3.1. They gave us a scale, and with this information, all right, let's just see with what we are given. They are saying use a scale of 10 millimeters to represent 25 meters per second to construct velocity diagrams of a two-stage velocity compounded impulse turbine, all right, with symmetrical blading at both stages, all right? So we dealt with a similar question like this where there is a symmetrical blading and that is affecting both stages in this case, all right? So here, let's see, according to the information that we are given, using this scale, divide by 10 here. So it means our scale is going to be 1 millimeter, representing 25 divided by 10, that's 2.5. So that's 2.5 meters per second, okay? Then the symmetrical blading at both stages, that is the angles at these moving blades are exactly the same, all right, for both stages. So theta 1 and this angle phi 1, theta 2 and what? Angle phi 2. So that is what you're given. So angle theta 1 is equal to angle phi 1, theta 2 and phi 2. They are equal. The mean blade speed for the turbine is 80 meters per second. You are given the mean blade speed, which is our U, is given as what? 80 meters per second. All right. While the nozzle speed and angle, so considering the part of the nozzle speed V1 and its angle alpha 1, that is the nozzle angle, is given. So that's our V1 from the nozzle, our nozzle speed, 450 meters per second, and its corresponding angle, which is the nozzle angle, is also given. So that's 20 degrees. Okay. Then we are also told that the absolute inlet second stage, take note, the absolute inlet. So I talked about this before when they refer to absolute angles. It's from absolute what? Velocities. From the second diagram, the absolute inlet is V3. So its corresponding angle is what? Alpha 2. If it is the exit, V4 as the absolute, its corresponding angle, beta 2. So that is the condition. So in our case, they said absolute inlet. So that's the angle what? Alpha 2 that we are going to consider since we are given for the inlet. So angle alpha 2 is given as what? Well, that second stage is given as 18 degrees, all right? And the coefficient of velocity across the turbine as a percentage, we can have that one as a decimal, divide by 100, 0.88. The mass flow rate through the turbine is given kilograms per minute. So divide by 60 to convert this to kilograms per second. That's going to be 75 kilograms per what? Per second. So we are asked to have that diagram, indicate all lengths in millimeters, angles in degrees. So this is what we have for 12 marks. Let us just try to have a sketch of how this was going to look like from what we are given? So these angles we are not given, but we are told that there is a symmetrical blading where we know that these two will be equal. All right, so according to the information that we actually have, I think here, guys, it was going to be wise enough for us to start with the first diagram. As we can see from that first diagram, we've got almost everything that we need, like to have the diagram at the end. All right. So that's from our first diagram. This is A, B, C, and D. We are given, so I'm going to indicate what you're given. We are given this U, this one. We've got this U. We are given this. The angle of phi 1, this one. The angle alpha 1, we are given. V1, we are also given. So that is actually enough for us to have this diagram, because the rest is going to be calculated from what we have. All right, so I'm gonna focus on the first diagram, then we use it to determine or to construct the second diagram. So that was what we had. All right, so let's see, according to the information that we are given, what we can do. So I'm going to focus on the constructions, guys. I'm going to focus on the constructions. Like I said, it is or it was easier for us to work from the first diagram. So from the first diagram, I'm going to draw the line A to B. All right, let's use our scale. 2,5. So divide by 2,5. That is going to give us 32 millimeters here. Divide by 2,5. V1 was going to give us 180 millimeters. So this one is a basic diagram, guys. Basic. Very, very basic. And these angles, remember, they are equal. Just the same here. So let's have our instruments for the constructions. All right, so here, what I'm gonna need is a ruler mostly. I need this and this. Okay. So from the first diagram, I'm working out from the first diagram. Let me just try to be close to the sketch so that we can see what is happening here, so that we can properly see what is exactly happening. So this is what you're going to have. Since we want the line AB, so measure 3,2 centimeters, which is the 32 millimeters. So measure. So that's from here, 0, 3,2, that's somewhere here. Okay, so this is our line AB. So this is what we are having as our AB, representing the mean blade velocity, our U, which is 32 what? Millimeters. Okay, so this is what we have. And we can see from the first diagram, from point A, using the angle and the value of velocity there, we can have this line AC. So we want to construct the line AC from point A at what? At the angle of 20 degrees here. We measure V1, which is what? 180 millimeters. So this one is direct from A like that. So you're going to measure the angle from A, 20 degrees from point A. All right, from this point A, we measure like this. So that's from this point, 20 is here, 0, 10, 20. This is our 20 at 160. So we're going to mark that point indicating what? Indicating 20. All right, then we have to join using the ruler here. So this is it from point A, joining through that point where we have got our 20 degrees. All right, so this is what you're going to have. This is our V1. The line that I'm drawing is representing what? V1. And V1 is what? Is 180 millimeters, which is 18 centimeters. So you're actually supposed to measure 18 centimeters. All right, so let's try to increase this up to 18 here. So I'm gonna join from 18 going this side up to point A. So this is what we have. This is exactly the point. This is exactly our 18 centimeters from A to this point. That's our 180 what? Millimeters, representing what? V1. So that's our point C, this one. So this is what we have. So that's our V1, which is 180 millimeters. We are at point C. So what we can easily do is to join these 2 points B and C to complete the diagram. Join these two, B to what? B to C, and measure that. Remember, B to C represents what? The relative velocity, our VR1. So you simply join and measure that. We have got what? Our VR1. Okay, so that's it. So this is our VR1, which we measure. It was going to be close to 150 millimeters, actually, 150 millimeters. Okay, so that is it. We can complete any other part that is remaining. Measuring of the angles, so forth. So remember here, we drew this one at angle, and this angle phi on this one, which was 20 degrees. We can measure this from our relative, all right? The inlet to the blade, this one, the inlet to the blade, that's our angle theta1. So you can also measure that, and that was going to be closer to 25 degrees. Our theta1, you measure that. So theta1, you measure, all right? But remember we said theta1 is equal to angle phi1 because of the symmetrical blading. So therefore, we have that one as 25. We measure that. So this is it. Again, we can see that from point C, we can actually have this flow velocity, a perpendicular drawn from that point C. So you're going to have the perpendicular from what? From C, it must be perpendicular to this horizontal line. It must be at perpendicular. Make sure, guys, it is what? Perpendicular. And you do measure that. You simply take this one at 90 degrees, it must give us exactly at what? At C. That's what I'm saying, perpendicular. So that's our flow velocity one. You measure that. Remember, that's our first diagram. So this is our first flow velocity. You measure approximately 6,3 centimeters, 63 what? Millimeters. All right, that's C to what? C to point F, our flow velocity, that's CF. Okay, so this is it. Let's finish the other part of the diagram from A, B, C. We are going to need this section A, B, D. So we are going to need this side. So we have advantage now because we have got the value of this. Remember, we said the angle phi and theta, They are the same. All right, let me remove this here. Remember, this is 25 degrees. Okay, so from that, we can have from B this side going to VR2. Remember, this is VR1. We are going to VR2 at an angle of what? At an angle of 25 degrees, since these two are the same. So what we need is simply to find what? VR2, just like that. So let's calculate our VR2 from our VR1. Remember, we've got the value of K. So V R2 is equal to K V R1, which is 0.88 times VR1. VR1 is 150. This is 150 millimeters. So that was going to give us VR2 from this calculation, which is approximately 132 millimeters. So we are going to draw that VR2. That's the line B to what? B to D. B to D from the point what? From the point B at 25 degrees. So that's it. So from point B at what? 25 degrees. That's from point B. You measure 25 degrees from point B, 0, 10, 20, 25, between what? 20 and 30 here. So that's somewhere there. Okay. That's somewhere here. This one. So let me join this and have the exact. Actually, I'm gonna find the exact value to use. Okay, that is the angle is what, 25. So we need something like 155 to get the exact diagram. No, 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 no. No, it's not going the direction that I want. 360 minus 180. Supposed to be, sorry for that, guys, 205 here. 205. So I have to change this one on my ruler here so that I can have exact things. So this is it. So you're going to join something like this. This is for exact values. That's why I'm doing this. So that I can have exact values. If I'm doing like this, guys, I'll be having exact values. So that's our VR2, and it is what? 132 mean 13.2 centimeters. All right, no problem. Let me just join, and from there, I'm just gonna increase that line, this one. So I'm just gonna extend it. All right, because we need 13.2. So I'm just gonna extend this line. Let's try to extend it. All right, so we have extended this. Let's go back and measure 13.2. 13.2. All right, so 13.2 is somewhere here. This is 13.2, somewhere here. That's 132 what? Millimeters. So that's where you're going to have the point what? The point D, from B to D. That is how it was going to look like. All right, so that's our VR1, then VR2. So this is our VR2, which is what? 132 millimeters. Okay, which was taken from what? From this angle phi 1, which is what? 25 degrees. Remember, these two, they are equal from the symmetrical leading. That's it. So we can see we're almost done. We just need to join A to D. Then we are done with this. All right. So A to D, you simply need to join these two, then measure that line which represents the absolute velocity, which is V2 at the exit there, V2. So that's our V2. You measure that. Okay, so you join. Then after joining, guys, like I said, you must measure. That was going to be 10.5 centimeters, which is what? 105 millimeters. That's our V2. You must have something approximately closer to that. You can also measure this angle at the exit, our angle beta. So that's our angle beta 1. You measure, it's going to be closer to 33 degrees. All right, so that's it. And also the flow velocity at the end. All right, so you guys are just going to use this one at the end, no problem. And also the flow velocity. I'm just gonna need the part of our flow velocity from the end at point D, perpendicular to this horizontal line that we are given. And you also measure that this is our flow velocity VF2 we measure. It was closer to 5.7 centimeters, which is 57 what? Millimeters. In what? In millimeters. So that's it. And what else? Let's complete again. Here we're gonna need the wheel velocity, the total wheel. All right, so let's just try to extend this a little bit going down. So guys, you must do exact constructions, all right? Exact constructions. If there is any part that you don't understand, let's communicate. That we can see that mostly it's from our N5. We talked about this previously. So from D to what? To C. That's something like this. Was going to give us the total wheel velocity. All right, so that's for the first diagram. Our total wheel velocity was going to be 256, 25.6 centimeters, which is 256 millimeters. If we measure this, right, closely, you must have a value closer to this one, all right? So that is for the first diagram. That is what we had from our first diagram. So what we're going to need now is to construct the second diagram. From the first diagram, we just need to take this one down. So I'm not supposed to change this, like to reduce the diagram because of the measurements. They will distort the measurements after. So that's why I'm maintaining the screen, wide open as it is like this. And, okay, but I hope you can see, guys, what we are having. This is how it was going to look like. So let's have our second diagram. So taking from our first diagram, we were going to extend from point A and B. All right. So that's here from A. All right. You extend that one from A going down. All right. So that's it. And from B again at what? 90 degrees. Directed B at what? 90 degrees. So that's it. Let's have our horizontal line to represent AB just like before. So this is going to be our AB. Same measurement is what we are given there. Same measurement. So let us just also consider our horizontal view here. Let us also consider our horizontal view because we're going to need this one later on. Okay, so that's approximately something like this. So this is it. We have this part representing AB from A to B of the second diagram. So that is the same as before, 32 what millimeters. Okay, so this is what we have. And on the second diagram, we have or from what we are given, we know this part of the symmetrical blading. We do understand this is to be applied, but we do not have that so far. What we are given for that is the angle, this angle, alpha to the 18 degrees. That is the only part that we can say we have this one. So what is that we can do? All right, remember the relationship between the velocities, the V2 and the V3 of the second diagram. So because we've got this angle, alpha 2, and V3, we can construct that diagram. We can see that. So if we can just obtain that, because this is our A and our B. So from A, this is the angle alpha 2, and this will be V3. So we need the value of V3 from the V2 of the first diagram. Remember, V3 can be what? Calculated as we have got the coefficient of friction. Our V3 is K times V2. So that is what you were going to do. You're going to calculate that from the given what? The given information. All right. So calculating our V3, that's 0.88 times our V2, which is 105. So that was gonna give us 92.4 millimeters. 92.4 is same as 92, just approximately 92.5. So you can take between 92 and 93, just 93, just in between. Yes, you can round off and just leave it as 93 or 92, or just in between, just take something in between. All right, of which you can use the value as it is. So here, I'm just gonna write this value on my diagram. Do not worry about that. So you just measure something in between 92 and what? 93, just as you know your constructions, all right? So that's our V3. We have it. So from 18 degrees at point A, let us measure that. All right, so point A, we're gonna need 18 degrees from point A. This is our point A here. So 18, that's 0, 10, 20, 18 just before 20, somewhere there. Okay, so somewhere here, this is our 18, somewhere there. So let's join from point what? From point A. We're joining from point A. That's what we need here from point A. Okay. So this is it. From our point A, I'm going to join this. Remember, we need something like 92, 92. So this is 9, comma 1, comma 2. So just between comma 3, just in between, just put somewhere there in between, guys, all right? So do not worry, guys. Just take something in between there, in between 9.2 and 9.3. That's where we have got. That's 92.4 approximately. That's going to be our point C, A to C, from our V3 that we are given. So here I'm just maintaining just the value, this one, because rounding off this, yes, we can round off, but just try to maintain it on your diagram, all right? This one is not an effect at all. It's not an effect, okay? Or you can write any value, guys. Do not worry about that. So, but you see how it was going to look like. Then B to C, just join that, all right? Complete that diagram by joining B to what? B to C. So joining B to C, and you measure that. Remember, B to C is a relative velocity that we are dealing with there. We are dealing with a relative velocity on the second diagram, which is VR3. So you measure that. That's your VR3. And you measure approximately, it was going to be around 6.2 centimeters, which is what? 62 millimeters. All right. So the rest, guys, is just to measure. We can also measure this second moving blade, this angle, theta 2. So theta 2, you measure that angle approximately 28 degrees. But remember, it is a symmetrical blading where theta 2 and this angle phi 2, they're equal. So we know that it's going to be what? 28 degrees as well. So that's an advantage to have the second part of our diagram, all right? So that was easy like that. And also the flow velocities here from point C going up. We're gonna need our flow velocity. So this is for the second diagram. So that's our VF3, right? Which you can measure approximately 2.9 centimeters, which is 29 what? Millimeters, the flow velocity. All right, so let's finalize our diagram. We are almost there. Just B to D, we finalize that. So we know that B to D is from our VR4. So this will be VR4, which we can find from what? VR3. All right, so let's find VR4, then we draw it at 28 degrees because this is also 28 degrees from our symmetrical what? Leading that we are given. So you see, guys, it was just easy like that. Easy like that, we are done. So let's have a 28 degrees along with what? VR4, along with VR4. So we need VR4 from VR3. All right, so that's it. VR4 K times VR3, where our K is 0.88 and our VR3, remember it is what? 62 millimeters. So that's 62 millimeters. So that was gonna give us VR4 approximately approximately 55. Let us just say 55 millimeters, all right? So that's our VR4. So at the angle of what? Phi 2, this one, the exit here of this second moving plate, at that angle of 28, you measure that. So let's start by the angle of what? 28 first at point B, all right? So at B here, you measure that angle, which is 28. So 28 closer to 30, somewhere there. All right. So our 28 somewhere here closer to this. So you're gonna join passing through the point. All right. So that's just something like that. We are done. We are done from here. It is just finishing up. All right. So let me see. I need the ruler, sorry. Okay, let me just get rid of these guys. To mean you just measure, guys, all these things. You just need to measure them. Okay. Why is it giving me something like this? Okay, I'll get this one. Okay, sorry for that. So this is it. So I'm joining from here to here, making that 28 degrees. Okay, so it's gonna be something like this. And we can as well measure, remember it was 55 millimeters. So 55 millimeters from what? From point B. That's at 5.5, yeah, approximately there. We have already taken that into measurement. Remember, it was what? 55 millimeters, our VR4. So VR4, that's to point what? To point D. So this whole part is our VR4, which we already measured, 55 millimeters, which was taken from this angle phi 2, which is what? 28 degrees from the symmetrical blending. So we can see that our diagram is almost done. What we just need is to complete it by joining A to D, making the absolute velocity V4. Remember, this is V3, so the exit there, which is what? V4. So that's our V4. Can as well measure that. It was going to be 3 centimeters, which is 30 what? 30 millimeters, taken at the angle what? At the angle beta 2, this one, which we can measure approximately to 58 degrees. You measure properly, all right? And also your flow velocity at the end from D, the perpendicular, that part of our flow velocity. From that, you measure as well the perpendicular that we have here from this point, which is our point E. This is E, this is F. So E to D, this one, D to E. You measure that flow velocity, that's our VF4, which was going to be 2.6 centimeters, 26 millimeters approximately, as well as our total wheel velocity from these two. All right. So here, let me just use this one, D and C. In between D and C for our total wheel velocity, we can as well measure that. That's our total wheel velocity for the second diagram. So we were simply going to measure approximately around 10.3 centimeters, which is 103 millimeters. All right, so that's it. We've completed our diagram. We have got everything as needed. Okay, so it was going to be something like this. It's only that I have to reduce so that you can properly see something of this nature. So you see, guys, it's all about revision. Remember these values when you actually use them. So it's all about revision, but your diagram at the end was simply going to look like this, right? Let's hope. Let's just hope you see it properly, something like this. Okay, so let's answer or attempt the other questions as we are given. 3.2, and use velocity diagrams that we had from 3.1 to answer this. 3.2.1, the relative inlet and exit velocity in the first stage. The relative inlet, what is entering relative, and that must be of the first stage. So the relative inlet, we have it, and the relative outlet, we have it, the exit. But they are needed in what? Meters per second. So you simply multiply by the scale. So 3.21 from the first diagram, is VR1, that's the relative inlet. So it's 150 millimeters. But remember the scale, 1 millimeter to represent 2.5 meters per second. So you have to multiply by what? 2.5. That was going to give us the value of VR1, 375 meters per second. And the exit is what? VR2. So VR2, 132 times 2.5 the scale, it is going to give us 330 meters per second, all right? So this is what you had, 3 point what? 3.21, Okay, let's move on. Another part, 3.2.2, the absolute exit velocity, the absolute exit velo and the exit angle from the what? From the turbine. Absolute exit, that absolute exit, it will be V4, which is at what? At this angle beta 2. All right. So that's what we need there. So V4 is 30 millimeters. So 30 times what? 2.5 our scale. That was it. It was going to give us 75 meters per second. And the absolute exit, considering that it's beta 2, which we measured, or you can measure, which is 58 what? Closer to 58 degrees. All right, so that was our 3.2.2, working with absolute exit. Absolute exit. That's from the final diagram at the second stage. Then the power developed by the turbine in megawatts. So remember, the power can be calculated from the mass rate, the blade velocity, then we're gonna need the total wheel. So this is total wheel of the first and of the second. Since if we use the mass, whatever that you're going to obtain is going to be in watts. If you use the mass rate in kilograms per second, the answer is going to be what? Kilojoules per second, which is watts. So to convert that watts to megawatts, you must multiply this by 10 to the exponent of -6, so that your answer will be automatically converted to megawatts. We are converting watts to megawatts. You multiply by the opposite, 10 to the exponent of what? -6. So that is what you're simply going to need. So the mass rate in kilograms per second, remember it was 75 from that division that we had here. We ended up with what? 75 kilograms. So that's our mass rate that we are going to use. All right, let's see if it's going to allow me to push it somewhere here. So that's our mass rate in kilograms per second, 75. You remember our U, it was 80 meters per second in meters per second. So we're going to take the total wheel for the first and second. So this is it, 256 and 103 in millimeters. 256 plus 103. So multiply by the scale, because this is in what? Millimeters. So we must multiply by the scale. 1 millimeter to what? 2.5. So we multiply by 2.5, which is to convert this whole part to what? Meters per second. So that's it. Like I said, if we want to convert this direct to megawatts, whatever that you're going to have as your answer here, multiply it by what? 10 to the exponent of -6. Your answer is automatically in megawatts. So whatever that you're going to have from this resultant is already converted to megawatts. So that was going to be 5,385 megawatts. As we are given that we must have our answer in megawatts, so you can just do the conversion straightforward, direct from what you are given. You can just do that conversion straightforward. All right, so as we can see, that is how these questions will be given as in the final exams. So it's just a matter of working out more questions, like doing more revisions, guys. It's all about more revision, all right? That can actually help a lot in answering or attempting any typical question, anyone, any that you're given. But in case there is any question that you are doing on your own and you do not understand that, all right, from what we have discussed and other questions that we have discussed, let's feel free to communicate on the comment section or to to post your question on the community section, as you can also upload from your side. All right, you can upload on the community section. So do that so that we can be on the same page in any revision to be done as we are preparing ourselves for the exams ahead of time.